Hello, I'm Dan Boniciolli and welcome to ChemSkills Podcasts. This is the 12th podcast in the series, and the topic of this session is electronegativity trends and the periodic table. Electronegativity is defined as the relative attraction of an atom for electrons in a bond. The first person to describe electronegativity was Linus Pauling in 1932, and he described it as the power of an atom in a molecule to attract electrons to itself. Pauling was able to calculate values of electronegativity for comparative purposes from bond dissociation energies, and since publishing these results, many other chemists have revised and modified these values to account for anomalous and peculiar behaviors that some elements exhibit within the periodic table. But his values have remained largely unchanged and are still used to this day. Here is a periodic table showing Pauling's electronegativity values, and when we look down group 1, for example, we can see that there is a general decrease in the value, and if we look across period 4, for example, from potassium through to krypton, we can see that there is a general increase in electronegativity. No electronegativity shown here for krypton and several of the other noble gases, but we'll discuss that in a later slide. Now, looking at the trends in more detail, studying the trend down a group, we know from previous discussions and previous podcasts that atomic radius increases because of an increase in the number of main shells. So the electrons that are involved in bonding, which are the valence electrons, the electrons furthermost away from the nucleus, are getting further and further from the nucleus as you progress down group 1, because the atom is getting bigger. So francium's electrons are much further from the nucleus than hydrogen's. This means that francium doesn't have as strong a hold on its electrons as does hydrogen, and so it won't draw electrons towards it as well as hydrogen does, and so we say that the electronegativity decreases. When you go across a period, and in this example from boron through to fluorine and again neon, a noble gas, doesn't have a value, you can see that the electronegativity increases. Now we know that the atomic radius is decreasing. The atomic radius from boron to fluorine is decreasing because the number of protons in the nucleus is increasing, but the number of main shells is not. And so the atom's getting smaller. So the electrons that fluorine uses in bonding will be closer to fluorine's nucleus than the electrons that boron uses in bonding, which means that being closer to the nucleus, fluorine will have a stronger hold on those electrons than boron. And having a stronger hold on the electrons means that fluorine has a higher electronegativity. So the electronegativity will increase as we move across a period. To summarize then, if the electronegativity decreases down a group but increases across a period, we'll find the element at the bottom of group 1, francium, to have the lowest electronegativity of the entire periodic table, and we'll find the element at the top of group 7, excluding the noble gases, which we will discuss in a moment, at the top of group 7, fluorine, to have the highest electronegativity. So electronegativity increases from bottom left to top right in the periodic table. Now the noble gases, they're not assigned values because if you will remember from the first slide, Pauling's values were calculated from bond strengths or bond dissociation energies. And since these noble gases are monoatomic, single atomed molecules, and since they don't easily form compounds and don't readily bond, it's very difficult to calculate electronegativity values for these elements. And so they're not given electronegativity values. But xenon here has been given a value of 2.6 because there are some compounds of xenon, and these are compounds of xenon bonded with fluorine, that values can be calculated from. And since publishing this periodic table, since publishing this data, some other noble gas compounds have been formed and some other electronegativity values have been assigned. But it's all academic really, because for all intents and purposes the noble gases don't react, so electronegativity values are not especially relevant for the noble gases. If we study the trend in more detail of some of the other groups, when we get to group 3, we can see that the electronegativity drops and then begins to increase again. Now, we know that the atomic radius is increasing, the atoms are getting bigger and bigger, but what these trends have revealed is that there are a number of other factors that obviously influence electronegativity, not just atomic radius. And some of these factors include things like shielding, include things like the shapes of the various orbitals that the electrons are in, relativity theory, the stability of the nucleus, etc. So a study of electronegativity has revealed some fascinating atomic features, and features that clearly have had an impact on electronegativity. Now, for all intents and purposes, a senior school chemistry student wouldn't need to know about relativity theory or nuclear stability, for example, and its impact on electronegativity. A discussion of the relationship between electronegativity and atomic radius is essentially all that is required. So I hope that this trend is clear. I hope that you've understood this podcast, and please join me again for future podcasts. Bye.